All right, today we are going to do some clever arithmetic, all based on the equal a priori hypothesis, meaning that if we have two systems that have the same energy level, there is going to be the same probability that those states will exist. So all of this is built on this concept. And from this information, just that one basic concept, we are going to derive the Maxwell-Boltzmann distribution. Too many ends. Energy distribution. So our starting point is going to be just like with classical thermodynamics. We are going to construct an arbitrarily contrived system. In this case, it's going to be an infinite reservoir at constant t. So it's just an infinite body like, I don't know, in a really big swimming pool, for example. Inside of which we're going to have two subsystems, subsystem A, subsystem B. Subsystem A is going to be at an energy of En. Subsystem B is going to be at an energy of Em. So the probability of system A, so PA of En, okay, so PA is the probability that subsystem A is at an energy state with energy En. The probability that A is an energy state at En, and then likewise, probability B of Em is the same thing, but just with the letter switched around. So if we look at the total system, if system A has energy En and system B has energy Em, then the probability of system A with this energy level En times by the probability of system B having energy level Em is going to be the same thing as the combined system having the same energy as the combined subsystems. We could also continue writing this in a number of different ways. Probability of the subsystem having, the total energy. This is also equal to the subsystem A having slightly more energy and subsystem B having slightly less energy. So all of these are equally probable because of the equal a priori hypothesis. So this is a priori means we have to assume it before we know it's right. Or equal a priori principle, I think is what they call it in the book. Okay, so we're going to assume in statistical mechanics, we're dealing with a finite number of particles. So we're going to assume that the energy levels is much larger than the number of particles. Meaning that every individual particle can be in a lot of different energy states. And this is actually going to be a relatively good assumption for anything unless we're getting to extremely low temperatures. So if you recall from last lecture, Planck's constant, that's the minimized quantized energy level. That was in the order of 10 to the minus 34 joule seconds. 10 to the minus 34 is very small. And in fact, when you had particle in a box, it was Planck's constant squared. Right, so the number of energy levels is, the step between the energy levels is very small. Which means we can assume that this probability distribution as a function of the energy is a continuous function, which it avoids us having to deal with any sort of infinite summations, and we can instead use an integral instead of a summation. Okay, so this next bit here, just bear with me for a little bit. Again, this is one of these derivations where we know the outcome after the fact, so we have to kind of muddy our way through these, a little bit of tedium. So we're going to explore this concept right here. Right? Let's say the probability of energy of subsystem A goes up a little bit, or the probability of subsystem B goes down a little bit. Now we can generalize that by looking at the slope of those systems. So if we take the derivative as a function of the energy of subsystem A, so En, with respect to the total system probability, play around a little bit with this. There's a little bit of a product rule in here. So what we're doing here is we're just expanding this. So this one here is relatively straightforward, right? So normally we just get dPAB divided by DEN, so the rate of change, the probability of the system having a particular energy with respect to the energy changing of subsystem A. We expand it to include the total energy, and this is just going to be equal to Now this last little step right here, this is because the energy of system B, EM, is not a function of En. So if I were to expand this one here, we would have DEN, which is 1, DEN, which is 0. So again, this is just clever arithmetic to get us to the end point. I'm glad I didn't have to figure it out. Okay, so likewise, what we're going to do is we're going to substitute this expression for a different form that we have here. These are all equivalent expressions. Then we're going to repeat the process, set the two equal, and see what we get out of the whole process. So if we repeat it, but instead we take the partial derivative with respect to the change of energy in subsystem A, but in this case we use a different functional form. Now we can do this step here because we're assuming that subsystem A and subsystem B are independent. Right? So for example, if I have a dice roll 1 and a dice roll 2, probability that 1 equals 1 and 2 equals 2 or something like that. Same concept here for probability. Now this is 1/2 of the product rule, right? We do derivative first times the second, first times derivative second, but in this case, the energy again of subsystem B is not a function of the energy of subsystem A, so that term goes to 0 as well. Yes?
Is there a reason why in the numerator of that, it looks like dP sub A, E sub n, that looks like a total derivative, and in the denominator it looks like a partial?
Oh, no, that's just my bad.
Okay.
So I try and keep the partials correct when you have multiples, but when you, yeah, no, that's just sloppy. No, this should be total derivatives as soon as you get it down to just one dependent and one independent variable. No significance there, just sloppy writing on my part. Okay. Now we can derive exactly the same expression here. So in this case, we could also write d, d, e, m. Oops. E, M. In this case, it would look a little bit different, right? This would be d, p, b, m. Don't do the partials on the bottom. Okay, so all I did was switch basically the a's and b's, and the process is exactly the same. Now this expression up here, if I were to swap out the n for the m, that's exactly equivalent as well. So this is the equivalent of d, e, m, p, a, b, n plus e, m. Are you with me so far? So every single one of these expressions is equivalent. This derivative is equivalent to this derivative because all I did was substitute in the two different ways to write the probability, meaning that these two are equivalent. There you go. And that's because these two are equivalent here. So that's how we tie everything together, just by cleverly writing out the probabilities. So we set these equal. In this case, we have well, now I'm just all confused with these partials and totals in this case here. I'll just do partials, I guess. Rearrange this a little bit, move stuff around, so we get move the variables over to the respective sides. Now, there's a blank, I left a blank spot here. Who remembers their partial differential equations? What am I doing here? What procedure am I setting up? This is a procedure to solve partial differential equations. Separation of variables. So this is going to be equal to a constant between these two relationships. Now, for convention, we call this minus theta as our constant. We can do one last little trick. Same thing we applied a little bit of times. Where we can, if we see something that looks like this, where we have 1 over the variable and then the derivative, we can combine them and say, you do this approach with, I think, the vapor pressure and the Clausius-Clapeyron equation. That's because the derivative of a natural log is the reciprocal of the function. So if you do the opposite, you can kind of slap them together. It's a nice little mathematical trick that makes things look a little bit more compactly. Okay, what do we think this function should look like here? When we integrate these expressions. Maybe it's easier to think about this one here. When you take the derivative of a function, you get out the reciprocal and 1 over it. It's an exponential. So in this case here, same thing holds true for B, but I'll just write out for A. So the probability of subsystem A being in an energy state with energy level En and this right here is the Maxwell-Boltzmann. Energy distribution. So what this tells us is that the higher the energy the system is in, the lower the probability you're going to be in that energy state. So it's an exponentially decaying function. Now, one other thing is that the summation of all the probabilities has to be equal to 1, meaning the system has to exist in some micro state. Now, if this is the case, that means our constant of integration, we're going to sum over all of the energy states. That's our constant. And the last thing that we'll talk about right now, well, not entirely true. We'll soon be discussing when we compare our statistical mechanics calculations to the macroscopic system size, that this variable beta is going to be related to the reciprocal of the temperature. So this is all it is sort of a clever calculus and application of the equal a priori principle. That's how we got to this point right here. So what we're going to do, this is our starting point for calculating macroscopic properties using statistical mechanics. We define this thing called Q, and we call it the canonical partition function. Canonical refers to constant n, number of particles, constant volume, and constant beta. In other words, we can think of that as constant temperature. Right? These systems here, closed, we'll assume they have a fixed volume, but their temperature and their temperature is constant based on the reservoir itself. The partition function is a statistical mechanics concept where if you know the partition function for a system, you can calculate all of its macroscopic properties through different clever kind of calculus arrangements. And so we'll go through today, provided I think we should have plenty of time to do this, we'll show how we can relate the partition function to the average energy of the system. But the partition function is the goal of StatMech. Once you know the partition function, you can solve everything. So in this case here, right, n, constant number of particles, v, constant volume, beta, constant temperature. So we define the canonical partition function is equal to the summation of all states I So if we have a particular energy state based on the number of particles in the volume of the system, scale that by the temperature, and this is the canonical partition function. So then we can write that the probability that system I will be in an energy state with energy alpha So in other ways, the partition function is the scaled summation of the energy of all the possible states. So let's ask a quick conceptual question here. What if temperature goes to infinity? Conversely, that means beta goes to 0. Now let's think about this first intuitively, and then we can look at it mathematically here. At infinite temperature, and let's define an arbitrary system so we can actually put some real world scenario into this here. Let's say we have a simple system where we have an energy of 0, we have an elevated energy of 1, and we have an energy of, let's say, 2, and we have 3 particles that are completely independent, right? So we could think of this as sort of thinking of electronic energy levels, or this could be velocities, right? Or this could actually just be like, weights in different bins at different heights, having different energy levels. So right now, if I have all 3 of them at energy equals 0, right? The energy of the total system is 0. I could have 1 up here, 2 up here, 3 up here, 1 up here, 2 up here, 3 up here, and there's lots of different combinations. So what the Boltzmann distribution is telling us is that the higher the energy of the system, the lower probability the system is going to be in that state, right? So it's less likely that all of the particles are going to be at the very, very top. So conceptually, let's say we have an infinite temperature. What is the probability of finding, what is the most probable configuration of the system at infinite temperature? Just conceptually. Okay, so a lot of people jump to that answer. Why is that one not intuitively the way to go about it? So what is the entropy of the system? I guess I'm jumping ahead a little bit here. Entropy is related to the total number of states, and we'll go into a little bit more rigor on that one here. So I'm jumping ahead a little bit to kind of demonstrate why we care about the partition function here. But the entropy is related to the number of states in the system. So right now, if all the particles are at the ground 0 state and I have 0 energy, we have an entropy of basically 1. If everything is at the highest energy level, that means we also have an entropy equal to 1. Which is not good. As you increase the temperature, you shouldn't be increasing the entropy, decrease the entropy. Entropy can never go down. So you can never get to a state where as you increase the temperature, the entropy starts to drop. So at infinite temperature, all states are equally probable. Right? So in this case here, e to the 0 is equal to what? Right, so e to the 0 equals 1. So the summation of all the states I of 1 is just equal to the number of states. So in that case there, the probability at t equals infinity is equal to 1 divided by the number of states. Right, so the probability of any particle being in any particular energy state goes to, it's completely flat and uniform. So at infinite temperature, all that it's saying is that the particles can choose to do whatever they'd like to do. They don't have to concern themselves with the individual energy levels associated with the system. At finite temperatures, there is a decreased probability to be in higher energy level states. So we jumped ahead a little bit with some other concepts, but they're concepts that I'm sure most of you have heard about in previous classes. Okay, so we can rewrite this expression here. This is the summation over energy states. But if instead we want to look at energy levels, right? P of I, this is the probability of being in state I, not necessarily the probability of having an energy level of E alpha. So instead we could write P E alpha is equal to the probability E alpha, whereas P I, probability of having energy state with E alpha, probability of having state I with energy E alpha energy. I wrote this really badly. So P of I is the probability of having or being in state I. I'll just try that again. Okay. Probability of being in state I with energy equal to E alpha.
So does that mean different states can have the same energy level?
Correct.
Okay.
So in this example here, if these are distinguishable particles, right, I could have particle 1 up here, particle 2 up here, particle 3 up here, right, and those would all have the same energy level, but they would be distinct energy states. Or another way to think of it here, so you could also draw this system out where you would have energy 0, energy 1, energy 2. You could have one particle in energy 2 down there, or you could have two particles at energy level 1 and one energy level 0. Those would have the same energy level, but they would be different energy states. So if we consider the concept here of the energy level versus the energy states, so we take the probability of being at an energy level of energy alpha. This is the degeneracy. Meaning the number of ways to be in that energy level. Be an E level, E alpha. This is the probability of being in an energy state with that level. So then we just substitute everything in. And it's basically the same relationship, but we have a degeneracy added in there. So this sets up two competing effects. As our energy level goes up for a collection of particles, there gets to be more and more ways that I can have that same energy level by all the different number of configurations. So you can kind of think of that as like the entropy of the system. But conversely, as the energy level goes up, you have a decreased probability of having that energy level or energy state being obtained. So if we combine these two effects together, if we plot out, so let's say, for example, we say, let's look at classical particles with a velocity. So let's say the energy of some state I magnitude is what matters. So let's say we have a total magnitude of the velocity. The energy of some state is going to be a function of its x, y, and z component velocities. So if we were to look at the degeneracy as a function of the energy, this is omega, this would be a parabola. The higher the energy you have, the more ways you can combine Vx, Vy, and Vz to all get to the same energy. Conversely, if we plot out the probability of finding your system in a microstate with an energy of EI as a function of the energy of that microstate, it's an exponentially decaying function. So if we combine these two and instead look at the probability of being in an energy level with energy EI, this is going to be equal to the product, or it's going to be proportional to the product of the degeneracy and the probability of being in that particular state. And there's also, of course, this partition function is built in there. In which case we get a distribution that looks something like this. And this is the velocity distribution for an ideal gas, qualitatively. But effectively, right, we can write out this function here as the probability of the gas is having a particular velocity as some pre-exponential factor, let's see, minus 1/2 mv squared. That is the Maxwell-Boltzmann distribution for the velocity of gases. Now this pre-exponential factor here is to ensure that this is gives you a uniform probability if you integrate over all possible energies. But all of this is basically contingent upon noting here that the higher the energy level you get to, the lower the probability. The higher the energy that you have, the more different ways that you can assemble the system to get those two. So you can kind of think of this as the interplay between the first law and second law of thermodynamics. And you can derive the probability distribution function for velocities of gas particles as a function of the temperature. Oh, I need to have KBT, my bad. Okay. Now, we're going to relate it to, we're going to tie this all back together. Partition function stuff over here. Okay, so we're calling the internal energy here the average energy, either per particle or for macroscopic systems we consider it as per mole. This is going to be equal to then obviously kilojoules per mole or kilojoules per particle. In fact, we have different units. We have units like ergs that are really, really small numbers to avoid having like really long, annoying scientific notation there. So that means we're going to write the internal energy as the average energy of the system, and oftentimes you'll see these little brackets. That means the average over all the possible configurations and all the possible states. And this is going to be a weighted summation. So it's going to be the energy of some particular state times by the probability that you're going to be in that state. All right, so it's just a weighted average of all the possible configurations of the system. So then we can write that as and right under Q here is, okay, it's just this Boltzmann weighted distribution of the energies. Let me rewrite it and actually make it clear. So if I take the partial derivative of the partition function Q with respect to beta, which we know is the reciprocal of temperature, what is the derivative of an exponential function? It's basically itself times by whatever junk is trapped inside of there. So this is equal to, oops. Okay, write it more clearly. Yes, sorry. Okay, so this looks really familiar to the top half. The only thing left that's lingering is I've got this reciprocal Q. So again, we're going to do exactly the same trick where I can bring in this q. So rather, let's see, if I set this equal to, then this is going to be equal to 1 over the partition function. Right, so the internal energy is equal to this, which is just equal to, oh, my bad, negative sign. Crap, there's a negative sign there. This is just equal to minus so let me rewrite that down here. The internal energy of the system, which is the average energy So this concept of a partition function, which is effectively a scaled summation of all of the different configurations the system can be in. So if I know the number of configurations the system can be in and the energy of those individual configurations, taking this clever partial derivative gives us the internal energy of the system. Seems magic and fantastic, but it ends up working out. Now this particular partition function was derived for having two subsystems all connected with an infinite constant temperature reservoir. Now if we were to modify the system and go through a very similar process, we can derive other partition functions as well. There's the microcanonical partition function, which is closely related to the entropy. There is the grand canonical partition function, which is closely related to the chemical potential. And so ultimately, the same way that we would use enthalpy, internal energy, Gibbs, or Helmholtz to help us solve thermodynamic problems, we can use different partition functions to help us solve different types of problems. The canonical partition function is one of the easier ones to work with. The microcanonical is another really straightforward one. And those are the two that we're going to focus on the most. Right, because the NVT system is kind of nice and convenient to work with. The microcanonical partition function is the NVE system. Right, so that's actually written like this. That's the next one we'll talk about. And this is simply just the degeneracy of the canonical partition function at a constant energy. All right, so we use this, I think I erased it, but we use the lowercase omega for individual particle energy states, or the degeneracy. The capital omega is for collections of particles. But this is the microcanonical partition function, and it's just the degeneracy of the canonical partition function. So in this case here, A and B don't necessarily have constant energy. A and B have constant temperature, and that's where we derive this one here. So what we're going to be doing is we're going to be doing a little bit of cheating. So then now we have a relationship between the partition function and the internal energy. We're going to then rely on what we know from classical thermodynamics, where we relate between different relationships between U and S and H and G, for example. And we're going to kind of cheat a little bit, and we're going to apply those same relations to the partition function. And then we're going to derive how we can relate the partition function to the pressure, to internal energy, to enthalpy, to entropy, to other different ones. And different ensembles have different relationships between macroscopic thermodynamic variables and the partition function on the statistical mechanics scale. But the goal of StatMech is to come up with these partition functions. So ultimately, everything hinges on, in the canonical partition function here, how do we determine what is the energy of an energy state? And how many different ways can we be in that energy state? So when we define an arbitrary system like a particle with multiple energy levels, we can then say, okay, how much energy does each energy level have? How many different ways can I pack X number of particles into Y number of energy boxes? Can the number of boxes, can I have multiple particles in each box? Right? That's the difference basically between a photon and an electron. Right? A photon is a boson. You can all be at the same energy level. A electron is a fermion, meaning you can't be at the same energy level, rather than you have basically two at the same energy level. But the idea behind StatMech is you just keep track of how many different ways the system can organize, what is the energy that the system can organize, and then we can draw relationships to macroscopic variables through this concept of the partition function here. More or less, StatMech is an exercise of tabulating different ways to write different energy levels. Okay. Hopefully the water gets a little bit less muddy as time goes on, and we can apply it to a little bit more of the problems. But basically, the first step is going to be deriving the ideal gas law from a quantum mechanical particle in box. That's going to be the first meaty application of what we're going to be handling here. Okay, so I will have office hours tomorrow. Chinmay will have them right now. Homework is due first thing. I'll be posting another homework very shortly. Exam is a week from Friday, so please be sure that you are confident in the homework solutions themselves. Okay. See you then.